Vanakkam. Now we are going to solve a problem from GATE 2016 Electronics and Communication Engineering Set 3 question paper. The question number is 44 and the question is, for the circuit shown in the figure, the delays of NOR gates, multiplexers and inverters are 2 nanosecond, 1.5 nanosecond and 1 nanosecond respectively. If all the inputs P, Q, R, S and T are applied at the same time instant, the maximum propagation delay in nanosecond of the circuit is. So here we need to find out the solution for this. Okay. We have drawn the circuit as such given in the problem, and some more details are added to this circuit to get the detailed explanation. Okay, let's get started. There are 5 inputs, namely P, Q, R, S and T. These inputs are applied at the same instant. It is given the NOR gates with 2 nanosecond propagation delay, NOT gate with 1 nanosecond propagation delay and MUX with 1.5 nanosecond propagation delay. So what is a propagation delay? It is the time taken for the digital circuit to respond after applying the input. In simple words, it is the waiting time to get the output after applying the input. Let's have a quick recap on the working of a MUX circuit. It is a combinational digital circuit, also known as data selector. It selects one data amongst many inputs and makes it available at the output. In this diagram, we have a 2 by 1 MUX, that is, we have 2 inputs and 1 selection line and 1 output line. Based on the input at the selection line, any one input line or data line is selected and that data will be passed or forwarded to the output side. So in this problem, this T input plays an important role. T input may be either 0 or 1. Based on this condition, we'll analyze the circuit with two cases. The first case is T equal to 0 and the second case with T as 1. So we start with case 1 and in this case T is equal to 0 and we switch on the power. So this P input is applied here to this NOR gate and this Q is applied to this NOR gate and R is applied here and this S is applied to this NOT gate and this T equal to 0 is applied to this selection line as well as to this NOT gate. Okay. So because of this T input, the selection input is equal to 0. So that means this 0th line, this input line is selected. That means it is open to accept the input, but this line is blocked. After 1 nanosecond delay, this NOT gate will provide a output and that is S dash. But this will be blocked at this first input line. And here also this NOT gate is supplying the output and that is nothing but T dash, that is equal to 1 because we have the input as 0. And this 1 will be immediately available at this S0 selection input. So that selection line will control this input line, isn't it? So here this first line will be selected and the 0th input line will be blocked. So this is happening after 1 nanosecond. So after 2 nanosecond, what would happen? This NOT gate will be supplying the output. We have the inputs as Q and R at the 0th instant itself. So after 2 nanosecond delay or propagation delay, the output becomes Q plus R the whole dash. And this will be available at the input. And this input path is open. After 2.5 nanosecond, we don't have any change from the previous condition. Only these outputs are available. This NOR gate supplies output, this NOR gate supplied output, and this NOR gate also supplied output. Okay. and this data is being processed and it is being forwarded. So after 3 nanoseconds, still the previous condition prevails and no change, and this data is still being forwarded because here the propagation delay is 1.5 nanosecond. So this data reaches by 2 nanosecond. So after 3.5 nanosecond only it will reach the output side. Okay. So when you have this 3.5 nanosecond, we get the output at the multiplexer number 1. So what is the output you get? We get the output as Q plus R the whole dash. The same input is forwarded here as the output. So this Q plus R dash is available at 3.5 nanosecond and immediately it is made available at this first input line, and no input will be accepted at this particular zeroth data line, zeroth input line, because it is blocked, because it is not selected. So at what time we get the input for the second multiplexer? By 3.5 nanosecond. So by 4 nanosecond, we don't have any other change because this propagation delay is 1.5 nanosecond. So we have crossed this 2 nanosecond plus this 1.5 nanosecond. That means 3.5 nanosecond. After that, it is going through this 4 nanosecond. Then 4.5 nanosecond, nothing would happen. Then 5 nanosecond, what happens? This Q plus R, the whole dash input is forwarded to the output side. It is available at the output side. Okay. So if you calculate this total, that is 2 plus 1.5 plus this 1.5, will get this 5 nanosecond. So for case 1, the total propagation delay is 5 nanosecond. Now let's move on to the next case. So now let's deal with the second case. Second case is t equal to 1. Second case is applicable when t is equal to 1. So at this time, we switch on the power so that these inputs are applied, and this t equal to 1 means the selection line is 1. So it enables or it activates this data line 1, and the zeroth data line or input line is blocked. This is what happens once you switch on the power. So after 1 nanosecond delay, what happens? This NOT gate will be supplying the output. So you will get this S dash as the output. This becomes the input for this first data line, and it started working. And this NOT gate is also supplying the output, so that is equal to 0. So this 0 will be the selection input. Because of this selection input as 0, the 0th data line will be activated. It is ready to receive input, but this first data line will be blocked. That's why we put a cross here. Okay, so that's what happening after 1 nanosecond. So what happens after 2 nanosecond? After 2 nanosecond, we'll get some output at the output line of this NOR gate. What it is Q plus R the whole dash because of NOR. Okay, NOR operation, but it will not be available. It cannot be supplied to this input line because it is blocked. And this data is being forwarded towards the output line, but it needs actually 1.5 nanosecond, isn't it? Already we had this 2 nanosecond over, but 1 nanosecond plus 1.5 nanosecond, that means 2.5 nanosecond is required to get the output at the output line of the multiplexer. So by 2.5 nanosecond, we get the output at the multiplexer. What it is nothing but this S dash is forwarded here. So this S dash now acts as the input to this XNOR. So now this XNOR is supplied with the two required inputs. One is P, the other one is S dash. But at the output side, this output will be available after further delay of 2 nanosecond. Okay, now this S dash is available here by this 2.5 nanosecond, but here it is blocked already. Okay, so by 3 nanosecond, nothing will happen because it is not yet being processed and forwarded to the output side. By 3.5 nanosecond also no change will be there. By 4 nanosecond no change will be there. But by 4.5 nanosecond, that means after 2 nanosecond delay of this NOR gate. Okay, in total it is 4.5 nanosecond. We can calculate like this: 1 nanosecond plus 1.5 nanosecond, that means 2.5 nanosecond, plus this 2 nanosecond, that means 4.5 nanosecond. Will get an output at the output line of this NOR gate, that is nothing but this P plus S dash the whole dash. So it is available as input to this 0th line. Now the time of this multiplexer starts. Okay, so from this 4.5 nanosecond, it will take 1.5 nanosecond to reach the output. Okay, so 5 nanosecond no change, then 5.5 nanosecond no change, still it is being processed and it is being forwarded. By 6 nanosecond it reaches the output, so you get the output as P plus S dash the whole dash. It is nothing but the data available at the input side. The same data is forwarded. Okay, so it takes 6 nanoseconds. So for case 1, when t equal to 0, it took 5.5 nanosecond, and when it is case 2, that is t equal to 1, it takes 6 nanosecond to reach the output. Okay, so the maximum propagation delay is 6 nanosecond. Okay, thank you.